So a curve. Okay, so we start with, first we have a vector functions or vector field. F equals to A is the magnitude in the direction of X, plus B is the magnitude in the direction of Y, and then C is the magnitude in the direction of Z. Or not necessarily the magnitudes. A could be a function, okay? Could be a function in X, and then B could be a function as well, okay? So it's in a vector field of three-dimensional, and then we said that the partial derivative of A, B, and C exists. Okay, so meaning that A, B, C are all function of X, Y, and Z. Okay, so we can do a partial derivative of that. Then the curl of F is equals to the vector field on a three-dimensional space. Meaning that you're going to produce another three-dimensional vector field. And the curl of F can be written as the partial derivative of the function C with respect to Y minus the partial derivative of the function B with respect to Z, and that will be in the X direction. And then plus the partial derivative of A with respect to Z minus partial derivative of C with respect to X, and that in the direction of Y, and so forth. Okay, so that is the curl of F. I'm sure you're looking at it. There is long equations to remember. Okay, so you don't really need to remember this. You can actually derive this quite easily in the next slide. Okay, so recall that we introduced the vector operator del, and del is the partial derivative with respect to X in the X direction plus the partial derivative with respect to Y in the Y direction plus the partial derivative of Z in the Z direction. And we talk about gradient just now. The gradient will simply equals to partial derivative of the function with respect to X in the X direction, with respect to Y in the Y direction, and so forth. In the curl of F is simply equals to the del function cross product with the vector field F. Okay, so this is actually our curl F. And we know that cross products, we can write them as a determinants. So determinants, the first row of my determinants is my unit vector. So we have my unit vector X, unit vector Y, and unit vector Z. Remember our del functions? Our del functions is equals to del over del X, X directions, plus del over del Y. So in effect, this is a vector. This is simply the magnitude, if you think of it. Okay, so del over del X is the magnitude of this vector. So remember, if we have two vectors, A cross B, and then we said that this is the magnitude of my vector A. And this is the magnitude, or I call it X, Y, and Z. Okay, so the same thing here. So my del, the magnitude is del over del X for the X unit vector, del over del Y in the Y direction, and then del over del Z in the Z direction. So all this here go into my second row because that is my vector for my del. And then the third row will be my vector field F. Okay, remember we introduced our vector field just now. This is my vector field. Okay, so we have A, B, C. So this go to the third row of my determinants. Okay, so to work out the curve, simply solve these three-dimensional determinants. And you can show that this will be equals to my equation 1 here. Okay, so if I were to solve this determinant, so that will be equals to A. So we cross out this, and then we take the determinant of this 2 by 2. And then the next one, so we go from plus, minus, plus, if you remember, working out determinants of a 3 by 3. Okay, so the next one will be negative or minus AY. And then we cross out this. So will be these columns here, these columns, and this column. Okay, so that will be determinant of del over del x, del over del z, A, C. And then plus my AZ, and now will be, and that will be these two columns here. Okay, so that will be my del x, del y, A, B. And then you just need to solve that 2 by 2 determinants. So this will simply equals to del C over del Y minus, okay, so this one here, del C, okay, over del Y minus del B over del Z. Okay, so this multiply this minus this multiply this. Okay, so that's the 2 by 2 determinants. And then if you go through all this, you should be able to show that that will be equals to this equation here, equation 1. My del C over del Y minus del B over del Z. And then times my unit vector x. And then plus the rest of the equations. Okay, so all you need to know or remember is this: how to set up these equations and then solve the determinants. Then you work out the curve of f. Okay, any questions? Still good? Still following? Okay, so that is what we end up with, which is my equation 1. So, as mentioned here, all you need to remember, curl of a vector field is equals to del cross product with the vector field. Okay, and then you just set up that determinants and solve that determinants, and then you can work out these equations or my equation 1, rather than trying to remember equation 1. Okay, a simple example here. I have my vector field f, which is a function of x, y, and z. So I can think of this as my A, this is my B, this is my C. Okay, so So the curl of f will be my del cross product with f. Top row unit vector. Second row is my partial derivative. And then third row will be my function a, b, c. Okay? And then the rest will be just solving this 3x3 determinants. Okay? So that will be just purely maths rather than or something you learn in matrix. Okay, so if I were to solve this, so I'll take a x, then will be del over del y, del over del z. This will be x, y, z minus y squared minus xz minus y squared plus and then carry on from there. I will have ax, that will be del over del y minus y squared minus del over del z x y z. That will be from this here. And then from this one, there will be minus and then the last one and then just solve the partial derivative, and then you end up with the curl of the function or the vector field f. Okay, so the next slides will show you how or what's the answer is. So you end up with minus y into 2 plus x in the direction of x, and then plus x in the direction of y, plus yz in the direction of z. And that will be my okay. Any questions about curve? Okay, so that's just the mathematics of it, how you solve it. Okay, so all we have done so far is just define what is curve and then do a simple calculation how to work out curve. So the gradient of a function f, we talked about gradients early on, gradient of a function f in a vector field, three-dimensional vector field. And we also compute curve just now. Okay, so there is a theorem that said that if the functions of a three variables that has continuous second order partial derivative, then the curve of the gradient is equal to 0. Okay, so this is a theorem. Okay, so the curve of a gradient is equal to 0. This is known as the first non-identity. Okay, so if a gradient of a scalar field, if I take a curve of that, that will be equal to 0. Okay, so this is my first theorem. Curve of a gradient of a scalar field is equals to 0. We know that the gradient of a scalar field is a vector. Okay, so we start off with a scalar functions, do a gradient, we end up with a vector. So vector, we can do a curve on that. So by taking the curve of that vector, that has to be equals to 0. Okay, so that's the first theorem. And then a conservative vector field, meaning that the one that has a gradient equals to a vector field. Then if I take the curve of that vector field, that will be equal to 0. Okay, so that is theorem number 1. So if I revert it or rephrase it, so I said that if f is conservative, then the curve of that vector field is equal to 0. Okay, so basically just reverting that theorem. So we know that conservative means that a gradient of a scalar function is equal to a vector field. So if I take the curve of that vector field, that will be equal to 0. Okay, so it means that what I'm saying is that this is equal to f. That is what it means by conservative vector. Okay, so I now take the curve of the f will be equal to 0. Okay, so it's the same thing. It's just that instead of saying that the curve of a gradient, I'm saying that the curve of a vector field, and that vector field is equal to a gradient of a scalar field. Okay, so that is rephrasing that theorem 1. So in a way, we can test the vector to see whether it is conservative, to work out that the curve of that vector field, whether it's equal to 0. So if it's not equal to 0, then that vector field is not conservative. Okay, it's only conservative if it's equal to 0. The converse of theorem 1 is not true in general. Okay, meaning that, in other words, not all curve of f equals to 0 will be conservative. Okay, so we come to another theorem. It's called if the vector field f is defined in a three-dimensional and the has a continuous partial derivative, then the curve of that vector field will be equal to 0. Then the vector field will be conservative. Okay, so basically they means more or less the same thing, theorem 1 and theorem 2. It's just that it's quantified that the vector field have to be in a three-dimensional space, and has a continuous partial derivative. Okay. So this is more important. The meaning of a curl. What does actually curl mean? Okay, so we talk about curl, we calculate it, we have a theorem relate the curl to the gradient. But what is actually curl? So the name curl is that the curl vector is associated to some rotations. So the vector field represents, if we represent that vector field with some velocity of a fluid, okay, then the curl of that is referring to a rotation force. So in this case here, if I have a vector x, y, and z, the curl of that function or the vector field relates to rotations around that point. So if curl is equals to 0, then there is no rotation, meaning that it doesn't rotate. If it's not 0, meaning that it will rotate. Okay, I think all this wording is still not very useful for you to visualize what is happening. So the best is to illustrate it, what it meant. Okay, so have you been to a river? You look at the water flow in the river. Okay, so at the center of the river you have the velocity of the water, the highest, and then going to the bank, then you will have no velocity, or the slowest, and then go to 0 and stop at the bank. Okay, so the velocity is the highest at the middle of the river. So if you have two banks and then river, and then flowing down the river, the velocity of the water is the highest right at the middle, and then 0 at the end. Okay, so this is an equation to model that flow or the velocity of that water flowing in the river. Okay, so V is equals to AX D minus X, and then unit vector of Y. Okay, so if this is my Y, no, this is my X. Okay, X, Y, and my unit vector is my A, Y. Okay, so it's in the Y directions. So if you look at these equations, D minus X, so when X equals to 0, then my V will be equal to 0, which is here. X equals to D. Okay, so if I substitute X equals to D, this equation is going to also be equal to 0. Okay, so this is one side of the bank, and this is the other side of the bank of my river. Right at the middle of my river, which is X equals to D over 2. So if I substitute D over 2 here, so V will be equals to A D over 2, D minus D over 2, unit vector Y. Okay, so this will be A D squared over 4 in the direction of Y. Okay, so that is my A D squared over 4. Okay, going away from this, it's going to start to reduce and then go to 0 right at the bank of my river. Okay, so that is how the velocity of the water along a river. So we want to do a curve of that. Okay, that will be Okay, my equations, no components in x, so x is 0. The only component in y, it will be a, x, d minus x, and then no component in z. Okay, so you can solve this curve. This curve will be equals to ax del x del z, no, del y del z, so it will be ax d minus x, and then this will be 0. Then minus ay, okay, x del z, 0, 0, obviously this is going to be 0, and then plus az, 0 ax d minus x. Okay, so if you look at this, my x components, so del y 0, that will be 0, minus del over del z, there's no z here, so this derivative is going to be 0 as well. So my az will be equal to 0. My ay, if I do this, just both 0, so this determinant is going to be 0 as well. So I only have a component in my az. And then that will be the partial derivative with respect to x of this function here. And that will be equals to az ad minus 2ax. Going to write it up here. So I can take a out, which is equals to d minus 2x in the z direction. Okay, so that is my curve. So what is actually means of this curve? So I'm not sure whether you tried this before. So if you put a plank at the river, do you know what happens to this plank? You put the plank on the river. Have you ever tried that? So at x equals to d over 2, my curve will be equals to 0. Okay, so if I put d over 2 here, d minus 2 times d over 2, that will also be equals to d. So this bracket here equals to 0, which means that the curve is equals to 0. So what it means is that if I put a plank here, that plank is just going to sail down the river, but it's not going to rotate. Okay, so it stays constant moving down the river. Is I put it right at the center of the river. Okay, if I put a plank of wood off center, off the middle of the river, you find that this, because the velocity of the water is different, okay, it's higher at this place, lower at this place. So this place, this plank will still move down the river, but it will rotate. So you're going to rotate around an axis. So the plank goes to rotate, but moving down the river, rotating. Okay, so that is your curve. So the curve is the measure of the rotations. So the curve is 0, which means that the plank we still drift down the river, but it doesn't rotate. But if you have a curve, so depending, so on this side, which means that x is smaller than d over 2, then meaning that if I substitute that into these equations, then this bit here, you get larger than d. Okay, so if x is smaller than d over 2, so 2 times something that is smaller than d over 2, and then you take d minus that we're going to be negative. You follow? And then my curve will be negative. Okay, so because the bracket they're going to be negative, and therefore my curve is going to be negative. So my del going to be some negative value. Okay, so a negative curve tells you that the rotation is counterclockwise. Okay, so it's going to rotate counterclockwise. If I take x greater than d over 2, then this bracket here is going to be a positive value. Okay, so if not convinced, let's say I take curve of v at x equals to d over 4, let's say. Okay, then this will be equals to a d minus 2d over 4 okay, that's the wrong way around. So this is positive. Okay, so it is depending on where the z-axis is. You're talking about counterclockwise or clockwise. Okay, so depending whether z is going into the page or coming out of the page. Anyway, the curve of a negative value is a counterclockwise, but in this case here, it shows that it is counterclockwise, but the curve is positive. So it's just the direction of x. Okay, and then so in this case it is positive. So here the curve will be negative. But if you put a plank here, you can see that here has a higher velocity over this side, and therefore this plank here will rotate clockwise. Okay, so one side from the middle, you're going to rotate one direction. On the other side of the river, you're going to rotate in opposite directions. Okay, so one side is positive, the other side is negative. And that's the meaning of the curve. Okay, so the curve is to work out the rotations, but the direction of the rotation is centered at the middle, and then it's pointing perpendicular to both x and y. Okay, so that is the curve is the vector field in the z directions. Okay, so it's in the z direction. Okay, so that helps you to visualize what curve is. Okay, so that is curve.